Hi dear students, I hope you all are doing great. So let us start our topic for today, which is state of a system. My dear friends, the state of a system is a condition of a system, okay, which is described by state variables. So my dear friends, the condition of a particular system is described by the state variables. What is the meaning of that? Let's understand. It means that if you change the state variables, like if you change the temperature, pressure and value, what will happen? The state of the system will also change. So my dear friends, I will write down here one small note. If we change the state variables, okay, the state of the system will also change. So my dear friends, the state of a system is a condition of a system, okay, which is described by state variables. So if you are changing the state variables like temperature, pressure and volume, then obviously the state of the system will also change. Let us understand it in a better way. Let's take one diagram here. Have a look, my dear friends. Let us suppose I have a system with me here. Okay, this is the piston here. Okay, my dear friends. Inside this closed container, let us suppose we have gas here. So here is a gas. Correct, my dear friends? So it's a closed vessel. And remember, let us suppose this wall is a diathermic wall, means conducting wall. Diathermic wall, or you can also say conducting wall. Means exchange of heat is possible from system to surrounding or from surrounding to system in this particular closed vessel, my dear friends. Let's have a look. We were talking about the state of a system. State of a system. And I told you that if you change the state variables, the state of a system will also change. Let us suppose I have the state variables with me. Have a look here. I have the state variables with me. So what are my state variables, my dear friends? Usually pressure, volume, temperature, internal energy, Gibbs free energy. All these things I will discuss little bit later. So let us understand how when these things will change, the state of a system will also change. And how does the state of a system change? The system can move from its initial state and it can move on to the final state. That means, my dear friends, if you change the pressure, the state of system will change from initial to final. If you change the volume, if you change the temperature, obviously the state of the system will change. At initial state, let us suppose pressure is low. And then you are increasing the pressure. So obviously initial state has low pressure and final state will have the high pressure. So that means the state of a system has changed, but in terms of pressure. Yes? And let us think that we are talking about this particular gas. Let us suppose this is the gas here. And we are talking about the state of a system, means the state of this particular gas. Gas at low pressure and gas at high pressure. Initial and final. Gas at low temperature and gas at high temperature. Yes? Gas with little volume and gas with more volume. That means you can change the pressure, temperature and volume. Yes, I know? And when you are changing the state variables, the system will go from initial state to final state. Yes, I know? Which means the state of system will also change. Don't think here that the state means here a system will change from solid to liquid or liquid to gas. No. Here the state is nothing but a condition. A condition with low energy, a condition with high energy. A condition with low temperature and the condition with high temperature. The condition with, least value and the condition with the maximum value. So that is the initial and the final condition. Okay. So my dear friends, I hope you have gotten the idea about the state variables right out here. Let's move further here. So I am taking a gaseous substance from here and I want to talk about the state of a system. Okay. In state of system we can have the initial state or we can have final state. So we are discussing about the initial state and the final state of this particular gas, because this gas is the system here. So my dear friends, this gas is the system and you are discussing about, so let me mention this gas is nothing but it's our system here. This gas which is inside. So my dear friends, let us use the state variables here. Let us suppose the initial temperature is Ti, that is initial temperature. Okay. Then I will increase the temperature for this particular system. Yes, by supplying heat. Okay, when I supply the heat, the temperature of this system will increase. So it will go from Ti to Tf, that is initial temperature to final temperature. That means when you are changing the temperature, yes or no, the state of the system is also changing from initial state to final state. And these two are nothing but they are your state variables. So these two are basically the initial state and the final state of a system. Okay, let me call the initial state of system. And this is final state of system. This initial state of a system is at low temperature. That means the less energy will be there, less kinetic energy will be here. And this is at high temperature, so more kinetic energy is here. So let me explain you here. Now what is delta T finally? The change in temperature. The change in temperature will depend upon T final minus T initial. So my dear friends, the change in temperature depends upon final temperature minus initial temperature. Yes or no? And we call it as state function. Delta T is called as state function. So this is nothing but it is the change in temperature. That is equal to final minus initial. So when you have changed the temperature of the system, its state has also changed. This state will be having low energy and this state will be having high energy when Tf is greater than Ti. Let us suppose Tf is greater than Ti. Final temperature is greater than initial temperature. That means the initial state of the system will have low energy and the final state of the system will have high energy. Which energy? Heat energy I am talking about. So finally, if we talk about the change in temperature, when system goes from initial state to final state, there is a change in temperature and that change in temperature will be given by Tf minus Ti. And here we will have a positive value because we know that the final temperature is greater than initial temperature. So this change will be positive here. Positive here describes that the temperature of the system, this particular system has increased, my dear friends. So now you have understood that if I am changing the temperature, yes, that means the state of the system will also change. And here the state is from lower energy, the system will move from lower energy to higher energy. I can decrease the temperature also. That means the system will go from higher energy to lower energy. Yes. If I increase the pressure, that means the system can go from lower pressure to higher pressure. Yes. If I decrease the pressure, that means the system will go from higher value of pressure to lower value of pressure. So whatever you are doing, yes, with state variables, if you are changing the state variables, the state of the system will also change. So remember that particular point. I hope you have understood. Please make note of this. So my dear friends, let's have a look here. The state of a system. I told you a system can move from the initial state to the final state depending upon the state variables. So let's talk about here state variables here first. Let's take on the first state variable here. Let's suppose that is temperature. The initial temperature of the system is Ti, initial temperature. And the final temperature of the system is Tf. So this temperature is nothing but it's a state variable. So I will mention here we are talking about temperature, and that is a state variable. Because of this change in temperature, when you are changing the temperature, the state of the system will also change from initial to final. And what is the total change in the temperature will be given by Tf minus Ti. So remember that particular thing. Let's take one more state variable here. Let's take one more state variable. Let's suppose I am taking the pressure. We can either increase the pressure for the system. For any gaseous system, we can increase the pressure or we can decrease the pressure. Correct? So let us suppose the initial pressure is Pi and final pressure is Pf. Then the change in pressure will be given as what? Pf minus Pi. Correct? In the same way, my dear friends, if we take one more state variable, here, let us suppose we will talk about now value. Let us suppose Vi is the initial value. That is the initial state of a system. That is the initial value. Okay? So obviously, after changing the value, we can increase the value for the system or decrease the value for the system. So we'll get the final value, and total change in the value will be what? Vf minus Pi. So my dear friends, you are knowing now the things that if we change the temperature, or if we change the pressure, or if we change the volume of a particular system, then the state of system will also change. It will go from initial state to the final state. I hope you are understanding, my dear friends. Now let's take few more quantities here which will describe the state of a system. So let us take few more state variables. How does the volume change? How does the pressure change? We will discuss about that in this chapter. So right now you only try to understand what are here state variables. So let's take one more state variable here. Let's talk about now G. G stands for Gibbs free energy. G is here Gibbs free energy. So we will discuss about Gibbs free energy in this chapter. So my dear friends, let us suppose this is the initial Gibbs free energy of the system. Let me change the Gibbs free energy of a particular system. So it will become Gf. Yes, I can increase the Gibbs free energy or I can decrease the Gibbs free energy. So what is the delta G now here? Gf minus Gi. And what is this delta G? This is the change in Gibbs free energy. Gibbs free energy. Okay. Now have a look here, my dear friends. Let's talk about now one more state variable. Let's take one more state variable as S. S stands for entropy. In this chapter we will discuss about entropy as well. So my dear friends, if S is the entropy, the initial entropy of the system, and SF is the final entropy of the system, then delta S, that is change in entropy, will be S final minus S initial. So this delta S is change in entropy of the system. I know that you will be having many questions in your mind. What is Gibbs free energy? What is entropy? What is enthalpy? Everything will be discussed in this chapter one by one. So here you only try to understand that they are state variables. So let us talk about one more state variable here. If we take a state variable here as H, H basically stands for enthalpy. H stands for enthalpy. Let us suppose Hi is the initial enthalpy of the system. Okay? And HF is the final enthalpy of the system. Then delta H is equal to what? HF minus HI. Final minus initial. So now delta H is called as change in enthalpy. Enthalpy is nothing but heat content, which we will describe in this particular chapter. So these are all, my dear friends, state variables. Gibbs free energy, entropy, enthalpy. They are state variables. Because when you change these state variables, if you are changing the Gibbs free energy from Gi to Gf, then the state of the system will also change from initial to final. If you are changing entropy from Si to Sf, then the state of the system will also change from initial to final. Yes? And finally the value, the change in Gibbs free energy, change in entropy and the change in enthalpy, it depends upon the final minus initial values. So remember that, my dear friends. Now there is a term, how do we change the entropy, how do we change the Gibbs free energy, how do we change the enthalpy, how do we change temperature, pressure, volume? That will be our point of discussion in this particular chapter. So right now we are only discussing about that if you change the state variable like pressure, temperature, volume, internal energy, yes or no, even enthalpy, entropy, Gibbs free energy, the state of the system will also change. The thermodynamic state of the system will change from initial to final. So please make note of this. Let us talk about one more variable here, state variable, that is internal energy. So my dear friends, this is again our state variable. If I change this state variable, that is internal energy, then the state of system will also change from initial to final. If you take internal energy, it can be denoted by either E or it is represented by U. So you can use either symbol E or U for this. So let us take symbol E. This is the initial, initial internal energy of the system. Okay, and this is the final internal energy of the system. That means I am changing the internal energy. If I don't change the internal energy of the system, then initial state and final state will be the same. Yes or no, my dear friends? That means EI will be equal to EF, and the change in internal energy will be how much? 0. So in order to change internal energy, let us suppose, we can either increase it or we can decrease it. There are many ways of changing the internal energy. You can heat the system, or you can remove the heat from the system. The internal energy of the system will change. Or you can apply pressure on the system. Yes or no, my dear friends? Or you can change the volume of the system. So there are many ways of changing the internal energy of a particular system. Now if you look here, this internal energy of the system at initial state is EI and at final state is EF. Yes or no? So when your state variable, which is internal energy, changes from EI to EF, okay, then the total change in internal energy will be given by EF minus EI, and this delta E is nothing but change in internal energy. And remember, this delta E can be also written as delta U, because there are two symbols for it, E or U. You can either use E or U for the internal energy. I hope you have understood, my dear friends, this thing. So dear friends, state variables now you have understood, and even you have also understood the state of a system, correct, which depends upon the state variables, correct. If we talk of state variables, I have written state variables are the state functions which describe the state of the system. We have explained it very clearly. Now let us talk about here now what is a state function actually. State function. Have a look here. I told you that state variables are the state functions. So let us understand what is a state function. A physical quantity whose value depends upon initial and final state of the system. Initial and final state of a system. Very simple, a physical quantity whose value depends upon initial and final state of a system. So obviously, my dear friends, if you talk about here now, temperature we know that the value of the temperature depends upon what? The change in temperature is taken as final minus initial. So temperature is a state function. Let's talk about now volume, my dear friends, already discussed. So volume, change in volume, Vf minus Vi. The value of the change in volume depends upon initial state and the final state of a system. So it's a state function. So temperature volume is a state function. And pressure is also a state function. So pressure will be, change in pressure is equal to P final minus P initial. So a physical quantity whose value depends upon initial and final state of a system. This is initial state and this is the final state of a system. Okay, my dear friends. So these temperature, volume and pressure, they are your state functions. Now let us talk about now delta E, that is change in internal energy, my dear friends, and that also depends on EF minus EI. Or you can write it like this, delta U, because E is the internal energy and U is also the internal energy, because different books are using different symbols for internal energy. Some books are using E and some are using U as internal energy. So same thing, it will become UF minus UI. So that change in internal energy is also the state function. Or we can say here change in enthalpy. So enthalpy is also a state function, HF minus HI. Then we'll go for the entropy, delta S, SF minus SI. Entropy is also a state function. Let's go for Gibbs free energy, GF minus GI. That is also a state function. So my dear friends, temperature, pressure, volume, internal energy, yes or no, enthalpy, Gibbs free energy, entropy, all these are which functions? State functions. And you know that state variables are the state functions. So you can also call them as state variables. And you can also call them as state parameters. So the value of, temperature, pressure, volume, internal energy, Gibbs free energy, yes, entropy, enthalpy, the values depend upon the initial and final state of a system. Yes or no? And when you change these variables, the state of a system will also change. Correct or not? So please have a look here and make note of this. So dear friends, let us talk about now path function. A physical quantity whose value does not depend upon initial and final state of the system. You have seen just now that state function is there. The value of state function depends upon initial and final state of a system. But for path function, the value of path function does not depend upon initial and final state of a system, but it depends upon obviously the path of the thermodynamic process. So means the value of path function depends upon the path of the thermodynamic process. It does not depend upon the initial and final state of the system. Okay? If it depends, then it will become a state function, but it does not depend upon the initial and final state. It depends upon the path of the thermodynamic process. Let's have a look. Let us suppose if any person, okay, starts from the ground floor, and these are the stairs here, and he moves from ground floor to the first floor, correct? And now the same person is using the lift, and through the lift he is moving from the ground floor to the first floor. Now look at this path. This is the path here. And look at this path. So this is the path, okay, which is taking the person from the ground floor to the first floor. This lift is also taking the person from ground floor to the first floor, correct? Here, a person is just climbing the stairs and reaching from ground floor to the first floor. Now here the person will be in the lift. A person will be in the lift and will be using the lift and will be moving from ground floor to the first floor. Correct or not? Do you think this path 1 and the path 2, do you think these two are equal? No, they are not equal. In which path more work is done by the person? Do you think a person is doing more work here in this path or by the lift? Obviously, when we climb up the stairs, we are doing more work because we are covering up more path. So our legs are doing more work when we climb up the stairs. But in both the cases, I am moving from ground floor to the first floor. And here in the lift, my legs are doing little bit of work while going into the lift and then while coming out of the lift. So I am doing just a little work, correct? So here my legs are doing more work and here my legs are doing very less work because here I am covering up more path and here I am covering up less path. So try to understand. So here if I have here potential energy will be, let us suppose this is Pi initial. This is initial potential energy of a person at ground floor. And this is the final potential energy of a person at first floor. So my dear friends, if I talk about change in potential energy, change in potential energy will be potential energy final minus potential energy initial. So this change in potential energy is nothing but it is a state function. But if I look at the work done by the person, okay, when it climbs the stairs is more, and the work done by the person when he enters into the lift and goes from ground floor to the first floor. So both the persons are not doing equal work. This guy is doing more work. So I will tell you, a person climbing upstairs is doing more work as it covers more path. So my dear friends, then I must tell that work is a path function. I cannot tell that change in work, look here, I cannot tell that change in work is work final minus work initial. That is a wrong statement because work does not depend upon the final and initial state of a system. Work depends upon the path. If you cover up more path, understand you are doing the more work. If we cover up less path, then it means you are doing the less work. So climbing upstairs means you are doing more work. But while going by lift from ground floor to first floor, yes or no, you are doing less work. Yes, I can tell you that if you climb, let's suppose there is a mountain. Let's suppose there is a mountain here. And if you are climbing the mountain straight up, so this is path number 1. And if you climb the mountain like this and reach to the top, so this is path number 2. So my dear friends, when you are climbing the mountain by path 1 and path 2, no doubt the initial potential energy, this is final potential energy. Potential energy, change in potential energy will be a state function. Final potential energy minus initial potential energy we can do. But change in work will not be the state function because work depends upon what? The path. Here a person is using a direct path. So this guy is using a particular direct path. So the work done by this person is very less. But look at the path covered by the person, second person. Yes or no? That is more. So more path you cover in a particular process, that means more work is done by you. I hope you are understanding, my dear friends. So remember that thing. Work is a path function, but your potential energy is a state function. because value of potential energy depends upon final potential energy minus initial potential energy. I hope you have understood, my dear friends. So remember, now examples of path function are your work and heat. These are the two examples of your path function. They do not depend upon the final and initial state. You can't write down the final heat minus initial heat. Yes or no? But you can't write down final work minus initial work, because work depends upon which thing? The path. It does not depend upon the final and initial values. Yes or no? Please mention this thing. Let us understand now types of thermodynamic processes. First of all, we have isothermal process. So remember, during this process, temperature is kept constant. Temperature is kept constant. So my dear friends, the T, which stands for temperature, is constant here in this process. So temperature is kept constant. When temperature is constant, understand the change in temperature, that is T final minus T initial, is 0. Because everybody knows when temperature is constant, it's not changing. That means Tf, which means here basically Tf will be equal to Ti, because temperature is constant. So initial temperature and final temperature will be same. So obviously the delta T, change in temperature, will be 0. Correct. So let's look at the isochoric process. In this chapter, when we study the isochoric process, what should we kept constant here? Okay, we should write down during this process. Okay. We have here volume. Volume is kept constant. So that means V is constant. That means initial volume and final volume both will be equal. That is Vi is equal to Vf. That means change in volume will be Vf minus Vi. That is nothing but, that is 0. So total change in volume will be 0 here. So obviously during this process, you have a look here, my dear friends. It's adiabatic. I told you about adiabatic. There is no exchange of heat between system and surroundings. During this process, no exchange of heat takes place between system and surroundings. So when there is no exchange of heat, that means delta Q, that means change in heat, yes, will be 0 or not 0, will be 0, because heat does not change here. But I told you last time that heat is not a which function? It's not a state function, it's a path function. So if it is a path function, I cannot write down delta Q. So that's why you have to write down Q only. And understand that the change, this Q stands for here actually change. Change in heat will be how much? 0. And even if you mention delta Q also, but understand that Q is not a which function? It's not a state function. It's a path function. So change in heat you can mention delta Q, no problem at all. Will be 0. Because no exchange of heat between system and surroundings. Now isobaric process. So during this process, pressure of the system is kept constant, or we can say the pressure is kept constant. So P is constant. That means there is no change in the pressure. That means delta P is equal to Pf minus Pi. Those both pressures, initial and final pressure, will be same because pressure is constant. So delta P will be 0. In cyclic process, what happens? In cyclic process, the initial and the final state of the system is the same. So in cyclic process, the initial and the final state of the system will be same. How? Let us understand that cyclic process right out here. So let us talk of cyclic process, my dear friends. So I told you in cyclic process, the initial and the final state of the system is the same. If I draw a graph between pressure and volume, okay? So let us see here, my dear friends. Let us suppose this point A is basically the initial state of the system. Try to have a look. So this line, if I am drawing right out here, which is parallel to the x-axis here, okay? Along this line, the pressure is constant. Then I will move down, let's suppose it as point B, take it as point C, take it as point D, and then finally go back to A. So my dear friends, you are starting from point A, and that point A is nothing but, let's try to understand, this is the initial state of the system. Then you are going through a cyclic process. If you see along this line, you will find out that pressure is constant here. Here the pressure is constant. Yes. If you see along this line from B to C, the volume will be constant here. If you see along this line C to D, again the pressure will be constant. So when pressure is constant, we call it as isobaric. But when volume is constant, we call it as isochoric. Yes or no? So it is isobaric process, isochoric process, isobaric process, isochoric process, because here also the value is constant along this line. So from A to B, we have which process here? Isobaric, A to B. From B to C, we have isochoric process, that is volume is constant here. And along C to D, again we have isobaric process, because again the pressure is constant. If we go along D and A, you will find out here volume is constant, so we have again isochoric process. So my dear friends, the initial state is A, and finally in how many steps? 1, 2, 3 and 4 steps, this process comes back to the initial state. So A is the initial state of the system. So I will write down A is the initial state of the system, as well as final state, of a system. During which process? During here cyclic process. Now I can tell you, my dear friends, when you start from point A and you end up at point A, that means you are coming back to the initial point. And I wrote here in cyclic process, the initial and the final state of the system is the same. And that is A here. So what will happen? Have a look. What will happen to the internal energy in a cyclic process? So remember, in cyclic process, yes, internal energy, change in internal energy will be what? 0. Why? Because in final internal energy minus internal energy, what is the final internal energy? You are talking about point A. Here also you are talking about point A, because final is A, initial is also A. So the change in internal energy will be how much? Come on, 0. What is the initial point? A. What is the final point? A. In this process you are coming back to the same point A. That means when your initial and final point is same, who is the final point here? A. Who is the initial point? A. So that means at point A, the internal energy is final and initial, both will be same. So change in internal energy will be 0. Yes? But now if you talk of work, work is not 0. Why? Because look here, this internal energy is nothing but it's a state function. It depends upon the initial and final state of the system. But work is a path function. And work done is not 0. Why? Because let us suppose this process is moving. First of all, it covers from A to B, the distance, then from B to C. then from C to D, and then D to A. So it covers this path. So what is the path covered by the process? So it covers a path from A to B, then B to C, then C to D, and finally from D to A. That means some path is covered there, and the work does not depend upon the final minus initial. It depends upon the path covered by the process. Does this cyclic process cover some path? Yes, it covers the path from A to B, B to C, C to D, and D to A. So a huge path is being covered by this process. So our work will not be zero. That means in this process, work is done. That some work is happening, because work depends upon this particular path. But change in internal energy is a state function. It does not depend upon path. It depends upon initial state and final state of a system. So when we know that initial and final state are same, so the change in internal energy is how much? Zero. So state function internal energy is zero, but work as a path function is not zero, because it covers the path. Yes? So remember that particular point, my dear friends. Dear friends, have a look here. If I talk about work, you cannot write down that final work minus initial work. Why? Because work is not a state function. Work is a path function. Yes? So this is not possible. Correct? So my dear friends, if I say here, change in temperature, final minus initial, this is correct. Why? Because temperature is a state function. So it depends upon, initial and final state of a system. But you can't write down work final minus work initial, because it is a path function. It depends upon the path of the process. It does not depend upon the final minus initial kind of things and all. I hope everybody has understood. May God bless you. Have a great time. Take care of yourself. Thank you.